Welcome back. This is Fundamentals of Micro Nanofabrication. I am Swayam from IIT Bangalore, and this is continuation of a lecture on chemical vapor deposition, which is in the module of additive processing. In the last lecture, we discussed some basic mechanisms of CVD. Specifically, we were talking about mass transport limited regime, reaction rate limited regime, etc. Today we will look at various practical implementation of CVD equipment, various terminologies that is used, for example, hot wall, cold wall, low pressure CVD, atmospheric pressure CVD, etc. And I would like to use those basics that we learned in the previous lecture and apply to these systems and understand the various advantages and disadvantages of these systems, right. So, let us get started. So, as the last slide of the previous lecture was the various types of CVDs that people have designed over the years, and let us take each of these one by one. So, the first one is hot wall versus cold wall. The basic difference between these two types of systems is the chamber temperature. So, if you look on the left, you have a substrate that is sitting inside a chamber. You have this gas input, gas output, that is all constant. The change between a cold wall and the hot wall is in this quartz chamber. So, this quartz chamber is currently being heated by a halogen lamp. Now, the halogen lamp emits in the visible region, and the quartz is transparent to visible region. So, the radiation that is coming from these lamps goes through the quartz wafer without heating it up and directly heats the polycrystalline wafer. Now, some amount of heat might come from this polycrystalline silicon carbide substrate to the chamber, but primarily the chamber is not heated on its own. So, as long as you can keep the substrate insulated from the chamber always remains cold. Compare that to the case of a hot wall reactor like on the right, where the whole thing is enclosed in a furnace with resistance heaters, and these resistance heaters are in contact with this quartz tube. So, the quartz tube also heats up, and then that quartz tube in turn heats up the gases inside, which in turn heat up the wafers inside. So, in this case the chamber remains cold, in this case the chamber remains hot. What are the advantages of this system? The thermal mass is fairly low, it is only the wafers that is heating up. So, if you want to change the temperature during your recipes up and down, it is fairly easy to do so, and it does not take too much time. You can in fact make, you can change the temperature of the wafer in a matter of seconds. However, there is a disadvantage, which is that the temperature is not uniform. The problem is actually from thermodynamics. The only way to guarantee that the temperature of the wafer is a certain way is to keep it in an environment where all the walls of that chamber are also at temperature T. So, this is what a hot wall reactor or a typical furnace accomplishes. Because all the walls of this chamber are hot, you can be sure that the wafer inside is also hot. But in this case, all the walls of the chamber are cold, only the wafer is heating, and this wafer will then radiate the heat out, and that radiation will be non-uniform, and hence the temperature of the wafer would also be non-uniform. The problem with the hot wall reactor approach is that it has a very large thermal mass. Not just the wafers are hot, but the the quartz chamber is hot, the resistance heaters are hot. So, in order to change the temperature, you now need to provide heat to change the temperature across all of this, right. So, temperature ramps are very slow. Often you cannot cool down a reactor faster than around 5 degrees C a minute or something on that order. The advantage, however, the hot wall reactor is the temperature is uniform. The advantage with the cold wall temperature is that the temperature can be changed very fast. So, it really depends on what type of growth you need. You need the ability to change the temperature, or do you need uniformity? The precursor consumption is another aspect. The precursor consumption in a cold wall reactor is typically very low, because the only thing that is hot is the wafer, while the precursor consumption in the hot wall reactor is high, because even the chamber is hot, right. So, the chemistry will happen wherever the temperatures are high. So, it will happen in the gas phase, it will happen on the surface, it will happen on the wafer, it will happen on the glass chamber. The hot wall deposition temperature rates are sometimes can be low, sometimes can be low. It really depends upon the design. The cold wall reactors, typically they are very high, and it again comes back to this precursor consumption argument. All the precursor is going to the one thing, which is the wafer, which is hot, so that hot wafer gets a lot of deposition. The number of wafers in cold wall reactors typically will have fewer wafers, just the matter of putting them in. It's very hard to put the wafers vertically. You typically have to put the wafers laterally, which means they take a lot of space, right? You can only put so many wafers for a practical length of a tube. While in a hot wall reactor, you can just keep your wafers, maybe I can show it here, yeah, you can just keep your wafers vertically, and that allows you to stack a lot of wafers in one shot, which means the batch is larger. Cold wall reactors tend to be a little more complex, partly because the temperature is a little more complex to measure, it's a little more complex to control. Hot wall reactors are simple furnaces which are very easy to get. The mechanism of nucleation, we will sort of discuss this later, but hot wall reaction can have gas phase nucleation. Cold wall reactors only have heterogeneous nucleation. When we discuss nucleation, we shall see that heterogeneous nucleation is preferable, especially if you are trying to deposit a thin film. Typically, hot wall reactors are used in low pressure CVD system, and cold wall reactors are used in atmospheric pressure CVD systems. What is LPCVD and APCVD is the subject of the next slide. Atmospheric pressure reactors, as the name suggests, tend to work at very high pressures. This can be at atmospheric pressure, slightly higher than atmospheric pressure, but or at least a few hundred torr type of pressures, right? This is a simplest CVD reaction we know how to reactor design because it doesn't have any extensive vacuum equipment, seals, anything. If you think about it, the furnaces that we are using for diffusion and oxidation were essentially APCVD reactors. I mean, there was no chemical vapor deposition, but the reactor design was fairly simple. These usually are, the growth is mass transport limited in these reactors, and that is partly because the pressure is so high. So, we already discussed that pressure is one thing that will increase your growth rate no matter what type of reactor you have, and since this is atmospheric pressure, which is high pressure CVD reactor, the growth rates tend to be high. Because these are mass transport limited, high growth rate systems, you also need to be very careful in the flow of the precursor. That boundary layer is a problem, right, because you are mass transport limited. Often this is a cold wall system because T uniformity, temperature uniformity is not that critical. The dependence is polynomial or weak. All you have to ensure is the boundary layer is consistent. So, temperature uniformity is not that much of a worry. Flow uniformity is very much a worry. Usually we use these for fast and thick depositions. So, supposing you want a very thick deposition, you do APCVD, or you want a quick, simple, cheap, easy deposition, you do APCVD. The reactors look something like like the way this is for example called a radiant barrel reactor. So, this is a cold wall tube, the chamber, there are some radiant heaters which are emitting IR or halogen radiation, and that radiation heats up the susceptor and the wafer. And if you notice, this is a barrel design such that each facet that holds a wafer is at an angle. So, that is what ensures that the boundary layer is consistent from top to bottom and gives you a uniform deposition. Some of these are vertical reactors where the gases come from the bottom and then flow laterally to do the deposition. Sometimes it is just a simple slanted susceptor on which you mount the wafers and do the deposition. In this case, if I am not wrong, in this case you have RF heating. So, in this case the susceptor is made of something conductive such as graphite. You put induction coils which have high amounts of current, and that induction coil then induces current in this conductive graphite, which heats up the graphite and does the heating. So, in this case also the chamber does not heat up, in this case also the chamber does not heat up. The other extreme is low pressure CVD systems. These systems are often used for semiconductor depositions, for high quality film depositions, and prima facie you would think that just because we are cutting down on pressure, we must be cutting down on growth rate, and to some extent it is true, but the impact on growth rate is less than you think, and this slide is to highlight why. So, if the pressure say is reduced from 1000 millibar to 1 millibar, so that is a 1000x reduction in pressure. And now, in order to achieve that, we must be putting a stronger pump or to just increase the vacuum in the system, and that would increase the gas velocity. So, the gas velocity would also be higher because you are pumping harder, right. So, harder pumping, let's assume, I mean, it really depends on the Reynolds number and few other details, but let's assume you are increasing the velocity by 100x, right? For a 1000x increase in, for 1000 decrease in pressure, the velocity flow has increased 100x. Now, these two things sort of counteract the effect on growth rate, and that is why the effect on growth rate is slightly minimal. So, let us keep going with the calculation. So, diffusion coefficient, which is inversely proportional to pressure, means that the diffusion coefficient would also increase by 1000x, right. The boundary layer inversely depends upon the density as well as the velocity. So, velocity has increased 1000x, but the density has fallen, velocity has increased 100x, but the density has fallen by 1000x because the pressure has fallen 1000x. So, overall the effect on boundary layer is that the boundary layer has increased 3 times. So, D has increased 1000 times, boundary layers have increased 3 times. So, what is your Henry's coefficient doing? The Henry's coefficient has increased 300 times, right. So, interestingly enough, your diffusion is now 300 times faster because your pressure has become so much lower, and that higher diffusion coefficient means the higher Henry's coefficient means that compared to the case of say 760 torr, which is high pressure regime AP-CVD, and now if you go to 1 torr, you would actually have a slightly higher H. So, this regime that you had before, which is given by blue, right, where at some relatively lower temperature, you would transport from surface reaction rate limited to mass transport limited. Now that you have increased the value of H, you have now gotten this longer range where you are surface reaction rate limited, and at some very higher temperature, you then become mass transport limited. So, your shape of your curve has changed, right. So, now you have a region where for a much larger range of temperatures, you are surface reaction rate limited. So, previously you were surface reaction rate limited only from here to here, but now you are surface reaction rate limited from here to here. So, that is what is being shown here, that in the blue case the reaction rate limited, you were limited by now you have a higher probability of being in a reaction rate limited regime than previously. And in the reaction rate limited regime, your growth rate depends the following way. So, it depends on the total pressure, which has reduced 1000x, but it also depends upon the Henry's coefficient, and that Henry's coefficient, as we just did, has increased 300 times. So, pressure fell 1000 times, Henry's coefficient increased 300 times. So, overall impact on growth rate was that the growth rate reduced 3x, right. So, even though the pressure fell 1000 times, the growth rate only changed by an order of 3. So, it is not a very strong reduction. Compared to AP-CVD, you do have lower growth rates, but not orders of magnitude lower growth rate. The other consequences is that there is a very strong dependence on surface reaction rate. There is a very strong dependence upon K, which is exponentially dependent on temperature. So, you are not so much limited by wafer uniformity, but you are very sensitive to temperature uniformity. You are not very sensitive to boundary layers, but you are very sensitive to temperature. You are not so sensitive to the flow of the gas, but you are very sensitive to temperature. That is why LP-CVD reactors typically are hot walled, because hot walled reactors tend to give more uniform temperature. So, this is what a typical LP-CVD reactor looks like. It has this chamber. The chamber is often has these resistive heaters. These resistive heaters heat up both the chamber as well as the wafer, and the wafers are vertically stacked. And they can be vertically stacked because even though the gas flow is happening, say, from right to left, it does not matter how the gas flow flows between the wafer. The boundary layer does not care. So, this wafer does not get any different deposition rate than this wafer as long as both of these wafers are at the same temperature. So, that is a great advantage of LP-CVD. So, if you were to compare AP-CVD and LP-CVD, once again you realize that AP-CVD gas flow uniformity is very important, while in LP-CVD the temperature is very important. In AP-CVD we are often mass transport limited, in LP-CVD we are often reaction rate limited. The wafer placement in AP-CVD is often parallel to the flow of the gas. In LP-CVD it is stacked axially. The precursor consumption in AP-CVD can be high. Why high? Because the growth rates are higher. Well, in LPCVD they tend to be low because the growth rates are lower. The precursor concentrations in LPCVDs are often higher, and this is partly to compensate for the lower growth rates. People just bump up the partial pressures a little bit. In APCVD they don't need to do that. The deposition rates are higher typically in APCVD, slightly lower in LPCVD. APCVD reactors are much easier to construct because of the lower pressure, the pumping, the reactor design, the Reynolds number design, etc. LPCVD becomes a little more challenging to make. Often these are used for semiconducting depositions, often APCVD is used for dielectric depositions. Just one slide on some further complications which we have not included or yet understood in the simple model that we have discussed till now. I will not go into any more detail in these, I will just highlight these problems and then move forward. So, one problem is of mass depletion. So, imagine you have a chamber, and in that chamber you have mounted 3 wafers. So, this is your first wafer, this is your last wafer, and the gas is flowing from left to right. And supposing this is an APCVD reactor, right. So, you have done everything right, it is a cold chamber reactor, etc. Now, the growth rate will depend upon the total pressure, the Henry's coefficient, which you hopefully have designed all right. However, it also depends upon this y, right, which y is the ratio of the partial pressure of this of the precursor. Now, as the reaction happens from left to right, and as the precursor keeps getting consumed, the concentration of the precursor will change. So, the concentration of precursor might be slightly higher here and might be slightly lower at the last wafer. So, even though you have fixed the boundary layer, you have fixed the gas flow dynamics, you do not have control over the exact partial pressure of a component simply because it is getting used up, it is getting consumed as it goes from left to right. And unless you control that change of, unless your usage is very small percentage of the total concentration. So, if you are flowing say 100 moles of silane and you are only using 1 mole of silane, then that mass depletion is very minimal, it is going from 100 to 99. But supposing you are flowing 100 moles of silane and you are consuming 90 moles of silane as you go from left to right. So, now the gradient can be fairly large, and that gradient can cause some non-uniformity issues. So, even if your reactor is very well designed from a gas flow perspective, because of depletion of the precursor, you might still see some non-uniformity. So, the way to do that is to flow a lot of precursors, a lot of excess of precursor, and use a very small percentage of the precursor. Of course, this causes a lot of wastage, which increases cost. The second thing is, supposing you are doing LPCVD, you have your chamber, you have stacked your wafers axially, and I have repeatedly said that the gas flow pattern in LPCVD to some extent does not matter, it is all about the temperature. However, again, if you look closely, the growth rate does depend upon the total pressure, the concentration of precursors, and the reaction rate limiter, right. The pressure along the tube itself may not be uniform, right. Now, we ignored this effect by me saying that in gases typically the pressures are uniform, but if you stack these wafers very close to each other, then it is possible that you create a non-uniformity in the partial pressure as you go from left to right, because the only way this area is getting fresh precursors and this area is getting rid of all its byproducts is by diffusion, right, because there is no active flow between the wafers. The wafers are placed very close to each other, there is essentially a stagnant layer here. So, even in an LPCVD reactor there is a little bit component of diffusion in axial direction, because in reality this is a 2-dimensional problem and not a 1-dimensional problem, and all these issues complicate the design of the LPCVD reactor. In real world, reactor design is a complex art, it requires a lot of fluid dynamic simulations, a lot of experience and a lot of institutional knowledge, because the details are complicated. With that, we come to the end of the flow dynamic part of the CVD reaction. We looked at how flow of gases affects. The next thing we shall look at is how does adsorption occur, how do surface reaction occurs, and how does the nuclei on the substrate actually coalesce together to form a thin film. So, the next so that will be next. See you then.